Okay, it's time for us to continue. And I realized actually for this one last topics we didn't cover during the lecture one, the first 1 hour lecture. So we will start from here today, of course, and from here then we will jump to the new topics today. And the remaining topics, the so-called electrical field lines, actually, first of all, the understanding is just some imaginary geometric lines which you can draw to help you visualize the distribution of electrical field E in real space. So this is a so-called electrical field line. So you can see the purpose of having this electrical field line is just to give you some way to visualize the electrical field distribution. So you don't have to just imagine in your mind. And of course, in order to fulfill this purpose, then there are certain, you can say, rules or principles you need to follow in order to draw those electrical field lines properly. And we have these 4 rules. The first is to say at any point the electrical field line at any point should be tangential to this electrical field E. Let's say here you have this kind of arbitrary electrical field line. Then at any point on this electrical field line, immediately you can tell, let's say at this point, the electrical field E at this point should be along this direction. That is the so-called E is tangential to electrical field line at any point. So basically, this will give you the direction of E, right? And the second point is to say electrical field line always start from a positive charge and ends on a negative charge. So if we based on this, the second point, and for the same electrical field line we just draw, then we can tell if this is a starting point, then here you should have a positive charge. And on the other end, you should have a negative charge. So this is the meaning of electrical field line always begins on a positive charge and ends on a negative charge. So actually, it should be based on these 2 points together. Then you can define the electrical field line, the direction of electrical field E at any point. And the third point basically tells you there will be never having 2 electrical field lines cross each other. And the reason for this actually is because of the first 2 points. And let's say if you have assumed you have this kind of 2 electrical field line crossing, let's say crossing at this point. Then if you just look at the electrical field line 1, based on the first 2 properties, you can tell this is going to be the direction of E, right? Well, if you do the same, based on, let's say, this electrical field line 2, you will find out another E at the same point. At the same point, you will have 2 E along different directions. Of course, this is physically impossible. At any fixed point, E must be fixed, meaning there can be only one direction. So this is how you understand you will never have 2 electrical field lines cross one another. And the final point is about the magnitude, is to say the number of electrical field lines or the density, that is the per unit area, should be proportional to the magnitude of E. Or another way to say basically is to say the density of electrical field line should reflect the magnitude of E. If you see more electrical field lines, that means the intensity, the magnitude of E is larger. So this is 4 rules you need to follow to draw electrical field line properly. Of course, then you can also do the opposite. If the electrical field line is given, then you can also, based on these 4 rules, to determine certain to derive certain understanding in terms of course, mostly in terms of the direction, in terms of the magnitude of electrical field E. So this is about electrical field lines. The general rules, of course, then we can come to some typical charge we discussed. The most simple scenario is the electrical field lines for 1 positive charge for 1 negative charge. So this is the electrical field lines. Again, this is going to be the starting point, right? You can see for positive charge, it must pointing away from the charge. While for the negative charge, it must pointing into the charge, right? And the electrical field lines should be uniform. So that is why those electrical field lines should be uniformly distributed along this source charge. And this is the case of 1 charge, 1 point charge. And similarly, we can do it, we can construct the electrical field lines for 2 charge. Whether these 2 charge the same polarity, positive, positive, or opposite polarity, 1 positive, 1 negative. So you can see basically these 4 rules all must fulfill simultaneously at any point, at any point. This example, actually, we have a very similar question in the tutorial. So here, I will not go into the detail. So we will have time to tomorrow during the tutorial to discuss the details how we can handle this kind of question. So this is pretty much all about this electrical field line. So you can see basically is this 4 understanding. And how do you use this 4 understanding? We can do it in either way. Either we ask you to draw the electrical field line based on the certain charge distribution, or we can give you the electrical field lines, and then you need to derive certain understanding of the electrical field E at a certain point. So basically, these 2 ways about this concept, electrical field lines. And the last lecture, I mean this video recording on that part basically is the key topics is the so-called Gauss's law and also the electrical potential. Well, for the Gauss's law here, I will just briefly go through the key points so that actually we can continue the discussion in case some of you may not have time to watch the video. So first of all, for the Gauss's law, the very first understanding you need to have is the most important application of the Gauss's law, or why we introduce the Gauss's law, is to give you a more straightforward way to determine the electrical field E when this charge distribution is complicated. Because in the first part, what we can do is we can determine this E based on based on either, let's say, one charge, or it is a finite number of point charge, 2 charge, 3 charge. We have this Coulomb's law, right? And we can also determine the E when we have this kind of uniform charge distribution. Uniform charge distribution. So we can do the, in principle, we can still construct a single point charge and then do this integration to find out the total, right? These are the 2 ways to determine E from the charge information, either finite number or infinite number of charge. But in reality, actually, the charge distribution can be more complicated. Let's say it may not be uniform, or it can be an infinite number of charge distribution. Let's say if it's infinite, like in this case, then simply you cannot do this integration. Or in another way, if we still follow the same logic of doing integration, then it's going to be integration from minus infinity to positive infinity. Physically, this is still valid, but of course, likely for this kind of integration, mathematically, you cannot find out the final solution. So that is why we need to introduce the Gauss's law to determine this electrical field E in a more complicated scenario. And in order to establish the Gauss's law, the new concept we introduced is the so-called electrical flux. And the so-called electrical flux is just the number of electrical field lines penetrating through a given surface. So you can see there are 2 parameters. One is the electrical field lines, and the second is the surface. So that is why mathematically this is how we define the electrical flux, the dot product of E, vector E and vector A. And here the most critical point is how you define this vector A properly. And for us, we always follow this convention of defining the vector A to be along the surface normal and pointing away from the surface. So this is how we define the vector A for a closed surface when we are using the Gauss's law. So if you can do this, then in principle, you can find out the electrical flux for any surface. And this is step 1. Then the step 2, the Gauss's law will tell you for any closed surface, the total flux through this entire closed surface equals this ratio directly, the ratio between Q in and this epsilon naught, which is a constant. And this Q in is just the total charge inside the closed surface. And of course, for the same, let's say for the same closed surface, we can also determine the total flux by using this. This is the so-called definition of electrical flux. So then you can build up this relation. This one equals this one. Both are the electrical flux penetrating through a closed surface. And this relation will give you, you can see basically now you can connect this E, you can connect this E to Q in, total charge inside the surface, not the individual charge or the charge distribution. You don't need to care about how many charge or how those charge distribute inside the surface. All you need to figure out is the total charge. So then you can tell it's going to be, more likely you can figure out this E. It's going to be easier. So this is the Gauss's law. And Based on the Gauss's law, of course, as I mentioned, the most important part is how you can use it to determine E. But at the same time, actually, we also can derive some very important understanding for those conductors in electrostatic equilibrium. So here, point 1 is the so-called electrostatic equilibrium means there is no net charge motion inside the conductor. While we say for each charge, if it's a conductor, then it can move freely. But the so-called electrostatic equilibrium is just to say, in total, there is no net charge motion. There is one charge moving in this way, then there is another charge moving in this way. So each charge, if you look at each charge, they are still moving freely, but in total, all this movement cancel each other. This is the so-called electrostatic equilibrium condition. And number 2 is for all our discussion within this course, whenever we talk about conductor, it's always conductor in electrostatic equilibrium condition. We don't talk about any out of equilibrium condition. Okay, so these are the 2 points. And once we have this kind of conductor, then we have certain understanding. These 2, inside the conductor, there is no charge, there is no electrical field. So this E is 0, Q is 0 inside the conductor. Of course, the detailed derivation, you should go back to watch the video, how we can derive these properties based on the Gauss's law. This is the first point. And the second point, if there is no charge inside the conductor, then of course the charge can only stay on the surface of a conductor. That is to say, for a conductor, it can still carry finite number of charge, but all those charges can only stay on the surface, not inside the conductor. And the third point is the electrical field E just outside the conductor surface is given by this ratio, and this sigma is just the surface charge density. And finally, E is a function of the local geometry. When you have this sharper point, then the density is larger at the sharper point, so the E is also larger at those sharper points. So these are the 4 properties, especially the first one, this one. Meaning whenever we talk about conductor, then this understanding should come into your mind immediately. And the second part is about this electrical potential. And electrical potential and also potential energy basically is a description of the same thing. It's still about this electrical field, but it's a description in terms of the energy. So it's a different aspect of description of the same physics. And we can build up those relations, let's say this potential difference and also potential energy difference. From E, we can build up this relation of V. Let's say here basically is to say, if you know this E from A to B, then this is the way you figure out the potential difference between A and B. That is so-called VAB. And similarly, we can tell this potential energy, electrical potential energy, UAB. Right? Well, this relation between potential and potential energy. Right? And here is a related concept, the so-called equal potential surface. That is actually the name is quite straightforward. Means you have a surface where for this entire surface, the electrical potential V is the same at every point on the surface. Let's say you have this kind of surface. If this is an equal potential surface, simply means this point V1, this point V2, this point V3, all are the same. All are the same. And this is the basics. And if we try to apply the basic relation to certain charge, the first case is the point charge or single point charge. Then we can derive the electrical potential V due to this single point charge Q at a location at this distance of R. We can also determine the potential energy when you have two charge. We have two charge. The electrical potential energy between the two charge Q1 and Q2. So you can see actually this is a little bit similar. This is a Fe, this is F. V is due to the only related determined by the source charge Q, just like E is only determined by a source charge Q. Only determined by one charge, one source charge. While for the electrical force, you must have two charge, Q1, Q2, right? And this is the case of point charge 1 or 2. And we can also move further to deal with the case of infinite number of charge. So this typical, the so-called continuous charge distribution, right? So actually you can see from here to here, the logic is the same. We have been doing this for the electrical field E, right? How we can derive this E due to continuous charge distribution based on E from a single point charge, right? Now here basically is you are applying the same approach for another parameter, right? Here you already have this V due to a single point charge Q. And from here, if you want to determine the V due to an infinite number of charge, what you need to do is to do this integration, right? So you can see the logic or the general approach is the same. It's just different parameter, and the starting formula is a bit different, right? And finally is this another property for a conductor in terms of the electrical potential. So which basically tells you for any conductor, the entire conductor always have the same potential. Any 2 points on this entire conductor, the potential is the same. This is a so-called equal potential for a conductor. Whether it is on the surface or inside the conductor, the potential, electrical potential V is the same. So if you combine this one, actually we can say when it comes to a conductor, we have these three most basic property. One, two, and three. So again, means whenever we talk about conductor, these three properties immediately you should come into your mind. inside the conductor, both E and Q must be 0. And the entire conductor, any 2 points, the potential is the same, not necessarily 0. It's just to say it's the same. It can be finite, or of course it also can be 0. So these are the basically the two topics. The first, the Gauss's law, and the second, electrical potential. So again, of course, you still need to go back to watch the video for some details. And today we are going to first finish the last topic about electricity, which is the capacitance. So here, first of all, so far we have been discussing how we can have a finite electrical field E, electrical potential V from a charge, right? Then another question we need to answer is, in practice, where can we store those charge, right? You must have something to store the charge. Then this charge can give you this E, V, U, or this kind of parameter, right? And this is exactly the so-called capacitor, the function of capacitor, which basically is a device to store electrical charge, And actually, this should be not, shouldn't be something strange for you. Your Apple Pencil, when you write, I mean, some of you are doing this right now. When you write on your iPad with Apple Pencil, basically it relies on this capacitor charging, discharging process. And on the screen of your iPad basically is an array of many, many capacitors. And of course, later when we finish all this introduction, you can try to figure out how exactly this kind of basic device and the physics can be translated into this the technology on your hand. First of all, the starting point, what is a capacitor, or how can you get a capacitor? It's very simple. From structure point of view, all you need to have is two conductors separated by an insulator. You have two conductors, conductor 1, conductor 2, and in between is an insulator. Then this overall structure is a capacitor. So that's it. So you can see it's all about the material type and also the alignment of different material. And while for this, the charging process, or how we can store charge inside the capacitor, actually the key process is just charge transfer from one plate to another. Let's say when you have this kind of charge movement, then it's the so-called charging process. And in terms of the amount of charge you can store, this is always valid. Meaning you have it must be one positive and another negative. And the value of these two must be the same. One positive Q, another must be negative Q. So this is some basic property. And of course, if you have, let's say you have this here, positive charge Q here, negative charge Q here, then you have these two charge. With these two charge, you will have this electrical potential E, electrical field E surrounding the space. Just like here, drawn by those electrical field lines. You will also have this electrical potential or potential difference. Potential difference. This is the delta V. The potential difference, let's say, between this metal and this metal. So you can see there are two key parameters when it comes to a capacitor. First is the amount of charge stored in this capacitor. In this case, is Q. So pay attention. When we have a positive Q on one metal and negative Q on another metal, we say the total charge stored in this capacitor is 1Q. Not 2Q, not 0. So it's just 1Q. And at the same time, another defining parameter is this potential difference between these two metals, the potential difference. And the ratio between these two, Q and delta V, is the so-called capacitance. And capacitance basically is parameters to quantify how much charge you can store for a given capacitor, or the charge storage capacity. This is how we define this capacitance by definition. And the most important part, of course, so far are just some basic parameter, basic definition. The most important part when it comes to a capacitor is you need to understand how the charging is done based on the electricity physics we discussed so far. So let's say we look at this kind of capacitor, two metal plate, let's say plate 1, and this is the plate 2. They are just parallel, the most simple configuration. Two parallel metal plate, and in between is just air. So it's a two conductor separated by an insulator. And initially, of course, we make it to be charge neutral. There's no charge stored in this capacitor. And if we want to charge this capacitor, of course, like what you did every day, you need to connect this one to a battery. And a battery basically is going to have a positive side and negative side, right? You make this kind of connection. And basically, you are charging this capacitor. Right? So now we need to go into the details how exactly the charging is done. First of all, let's assume the voltage supplied by this battery is, let's say, delta V. Of course, then this delta V, it should equal to this V plus minus V minus. Right? The potential difference between these two, the positive end and negative end. Right? So this is how we define the potential, the voltage supplied by a battery. Right? And initially, of course, this V1 should be how much? Initial, before you charge the capacitor. What is the potential? Electrical potential? Should be 0, right? There's nothing. There's no charge. Right. And now you are connecting this metal plate to the positive side of the battery, of course, through a wire. right? It must be a metallic wire, this one. Otherwise, of course, you cannot charge it. So what will happen? When here is potential is 0, here is a positive potential. There will be a potential difference, right? And once you have a potential difference, you will build up electrical field E, which pointing from high potential to low potential. In this case, here is high potential, here is low potential. So you will have this kind of electrical field E pointing along this direction, right? Of course, everything happens only inside the wire, right? And if you have this finite E, everything again, here is metal, is a conductor, means there's a lot of free electron, right? So there will be free electron also on the wire. So what will happen to those electrons? There is a finite E electron, of course, it carries this charge minus E, finite Q. So all those charge, there will be a force along this direction for all the electrons, right? That is to say, the electron is going to move from this plate to this side, right? And if this happens, so eventually, then for this plate 1, it will carry positive charge. It will carry certain positive charge, right? Because simply some negative charge move away, right? So this is what will happen to the plate 1, and we can do the same analysis for the plate 2. Now for the plate 2, initially, here is 0 potential, here is negative potential. So now it becomes high potential, here high potential, here low potential. So you will have this E along this direction. And same thing for the electrical force is going to be along this direction. Again, we are only talking about electron, which carries a negative charge, right? So then, eventually, you are going to have some net negative charge on this plate, right? So now you can see, basically, you can have some positive charge on one plate and negative charge on another plate. But of course, again, you know, at a certain point, the so-called your device will be fully charged. That is to say, the charging process will stop at a certain point. So now, if based on the analysis we just did, can you tell me what is the defining condition for the capacitor to be fully charged? What is the defining condition? Let's say in terms of E, F, delta V, which one to be 0? Delta V. Delta V means, so here the delta V we are talking about, is this is the delta V. Are you saying this delta V should be 0? So we can do it step by step. Again, the immediate driving force for the charging process is here. It's this one and this one, right? This is the immediate driving force. So of course, if you need to say fully charged or the charging process stop, then of course you need to stop this. You need to make this F to be 0. If F is 0, then E should also be 0, right? And if E is 0, basically is to say there is no potential difference between the two ends. While for the battery, this end, of course, is fixed by the battery itself. Then means the potential on this plate should be V plus. Then the two ends of this wire, the same potential, there will be no E. E is 0, F is 0. Then there will be no more charge transfer. And similarly, for this plate 2, eventually it should be V minus, same as this end. So then there will be no delta V, and also E and F going to be 0. Right? So that is to say, when the potential difference between these two plates E equals V plus minus V minus, that is here. It's here. It's delta V. When this condition is reached, then the charging process are finished. Right? This is a so-called defining condition of having the capacitor fully charged. Right? And here is basically just the analysis we did. We can just skip those slides. So finally, you can see this is the delta V, and this also must be delta V. And if you have this to be delta V, of course, you can also determine the E in between the two plates. That is E, right? And now if we have this relation between delta V and E for this kind of simple parallel capacitor, yes? Delta V, you mean here? No, it's not 0. Here, this one? No, the delta V from battery is fixed. No, it's just the voltage you can get from your battery. Let's say 1.5 volt. The value you see when you buy a battery, there's a initially is 0. Yeah, you charge it, and once it's fully, the capacitor is fully charged, and then there will be a potential difference on this capacitor. And that potential difference is going to be the same as the battery. And here, if we are looking at this kind of simple capacitor, again, the so-called simple capacitor is just two parallel metal plates. Two parallel metal plates. This is the most typical structure. And we can actually further derive the capacitance in this formula. So again, pay attention to this difference. This formula applies to any capacitor. 1, and this 2 applies only to this parallel capacitor. This is, of course, in practice, actually, most of the time we are dealing with this kind of parallel capacitor. Means actually most of the time you can use this one. You can use this one. Okay, next, actually once you understand how the charging is done for a capacitor, and for the remaining topics about how we can determine the equivalent capacitance of multiple capacitor. Actually, it's quite straightforward. Let's say here you have two capacitors connected. This is the so-called connected in parallel. C1, C2 connected together to this battery. And we can follow exactly the same analysis to derive some relationship. Let's say, again here I will do it again, but for this next scenario, this capacitor connected in series, later you can do it by yourself. Again, let's say here we label this as V1, V2. So then delta V equals this V1 minus V2, right? And we can make this delta V, this V1 to be a positive value, this V2 to be a negative value, again because of these two ends of the battery. And initially, of course, it's all 0. V is 0, and here is all 0. Right? So you will have this V, delta V along this direction, and also E along this direction. And the same, you will have here delta V. Sorry, I should use, let's say here, I use delta V prime, delta V2 prime. And also, here is going to be E, let's say here E1, E2, right? And then there will be F1. There will be also F2, right? That is to say, this is how you get some positive charge here, some positive charge here, and some positive charge here, right? And similarly, on the other side, you will get some negative charge here, and some negative charge here. This is pretty much, we are repeating the analysis for these two capacitors. But now let's look at this relationship in terms of the delta V, in terms of charge Q, in terms of this capacitance C. First of all, we can define this so-called fully charging condition. That is to say, this one should be 0. This one should be 0, right? If these two are 0, then here is V1. This V1 is supplied by battery, so it's going to be fixed. Meaning, finally, here is going to be V1. Here is also going to be V1, right? And the same for this plate is going to be V2, and this plate is going to be V2, right? And if we define this delta V1 is a potential difference for C1, it's just V1 minus V2, right? And the same for the delta V2, the potential difference on the capacitor 2. And all equals this delta V, right? Then you can build up this first relation in terms of the potential difference, right? And the second one is the total charge. Let's say, so I will write down here. So this is the relation 1, and for the relation 2, now we are trying to figure out how many charge are stored in these two capacitors together. the total charge stored on these two capacitors, Q should equals, you can see, the so-called total charge. The source of the charge must come from the battery, right? And you can see, if you look at this negative side, basically, some charge is moving to this capacitor, and some charge is moving to this capacitor. And this, let's say, is Q2. And this is Q1. So then the total charge stored by these two capacitors together, Q must equals Q1 plus Q2, right? That is to say the total charge transferred from battery to these two capacitors together is Q1 plus Q2. So this is a relation in terms of the charge. And if you combine these two relations, of course, for each capacitor, let's say capacitor 1, you still have this relation by definition. And this relation also by definition for capacitor 2, right? These are always valid for any capacitor, as we just mentioned. And if you combine all these 1, 2, and let's say 3, 4. Of course, here 3, 4 are nothing special. It's just the definition, the relation by definition for these two capacitors, right? And you will find out, so here is the Q total. You will find out this total capacitance, or you can say equivalent capacitance of these two connected in parallel should equal C1 plus C2. C1 plus C2. Basically, this is a C1, this is a C2, right? And actually, if you can expand this connection to have another capacitor also connected in parallel, you do the same analysis, you will find out this is a formula to give you the equivalent capacitance for multiple capacitors connected in parallel. C1 plus C2 plus C3 plus C4 all the way. And here, the connection in series, I will leave it to you to figure out basically the key relation. This is the first key relation, and this is the second key relation. And on top of this, again, you have these two, always have these two. So you try to figure out this 1 and 2 for the two capacitors connected in parallel, in series. And with this, you can also figure out this is a formula to give you the equivalent capacitance of multiple capacitors connected in series. And actually, in the test, in the exam, this is going to be, for sure, we are going to test, is how you can determine the equivalent capacitance of multiple capacitors. Of course, the key is you use these two relations, this one and this one. But of course, this will only give you this equivalent capacitance in order to, let's say, determine some relation in terms of potential difference, in terms of charge. You will also need to understand, let's say, this relation 1, relation 2. This is the most important part for this topic, to determine the relation or the equivalent capacitance for multiple capacitors. Well, some other relatively minor topics is this dielectrical constant, which basically, if you change the insulator in between, you will also change the capacitance. Typically, we are talking about the insulator being air. There can also be some other insulator. And here, the key parameter to define the difference is the so-called dielectrical constant, this kappa. And this one basically is equals 1 for air or for vacuum. So you can see when you change this insulator from air to certain insulator, all you need to consider is this dielectrical constant when it comes to the, this capacitance. Here is just a table for typical dielectrical materials. I think this one we can skip. And another concept is the so-called energy stored in the capacitor. Again, here, actually for this part, is also mostly for you to have a brief understanding, although you will also see equations or formula. You are not required to do any calculation for this part. Yes? You don't need to remember anything. We will provide a A4 paper where you can basically all the formula you need, you will find from there. Mm-hmm. So here is actually to understand how where this energy comes from for a capacitor. When let's say it's charged, where does the energy come from? The way we understand actually is, if it's a capacitor, then we can, of course, we know there will be Q, there will be delta V, and the ratio is C, right? And the so-called charging process, as we just mentioned, initially both is 0, the charge is 0, and the final state, let's say, the charge is Q, then another must be minus Q. So what happens actually is just from this state to this state, from here to here, what happens basically, you move charge Q from here to here, let's say electron. Then eventually you will have here minus Q, here positive Q, right? And of course, then this process will accumulate certain energy, electrical potential energy between these two conductors. So now we can look at actually in this way, if from here is minus this Q minus Q. We just look at this movement of tiny charge delta Q. So in one case, it will be Q plus delta Q, another minus Q minus delta Q, right? And from this, okay, now let's look at, yes? Yes. You just do one of, let's say, yes, in between you have, of course, as you can see, you need to connect this to an external circuit so you can do the charging. Let's say connect to a battery, then you can do. It's not to say you only have these two capacitors, you can charge it from nowhere, of course, no. Yes, yes. It's not directly, but effectively we can consider it in that way. It's not directly to say this charge moving from this one plate to another plate. It's still through let's say through a battery. the battery is kind of reservoir for charge. Then, yes. No, we can still go back to here. Then you can see actually how does this charge move happens. Positive charge, so you can see for the left side actually is a charge moving from the capacitor to the battery. For the negative side, it's a charge moving from battery to the capacitor. So effectively, then on one side, on one plate, you have positive charge. On another plate, you have negative charge. Yes, so you can see it's kind of still is a loop. So here, basically, if you consider the state 1, which is just Q minus Q, and state 2, okay, let me just write down here, this is Q minus Q. This is state 1, and state 2 is Q plus delta Q, and here is minus Q minus delta Q. So from state 1 to state 2, actually, we can tell the energy accumulated, the extra energy accumulated actually should equal to this. Delta V times delta this dq. This dq basically is to say the charge you are moving from one plate to another plate. And because between these two plates, there is a potential difference delta V. Then, in order to move this delta Q from one plate to another plate, this is the work you need to do. Or another way to say this is going to be the energy accumulated inside the capacitor. And if you are looking at the total charge, that is to say from 0 to this final state, basically is to say this delta Q should initially 0 and finally is Q. So this is the meaning of how you can figure out the total potential energy accumulated in a capacitor. So finally, you will have this formula. Again, for these slides, still we discussed briefly, it's just to give you an idea how you understand the energy accumulated in a capacitor, where it comes from. You don't need to do any calculation for this. And the example actually is very typical, as I just mentioned for sure. This is something you need to be able to do to determine the equivalent capacitance of multiple capacitor. Well, those multiple capacitor can be connection, some connection in parallel, some connection in series. Let's say in this case, you have in total, you can see 6 capacitor, and the way you do it is you simplify the circuit step by step. Like in this case, first you can identify these two are connection in parallel. Then you can find this equivalent capacitance. Similarly, for these two, you can find the equivalent capacitance. Step 1, and you can repeat this. Let's say for these two now is connection in series. You can reduce the circuit to one capacitor and find out its capacitance. Similarly, for these two, and one more step, you can find out this final one equivalent capacitor and also its capacitance, right? And for the value, of course, typically the value is quite simple. So confirm you can do it? It's still okay. And of course, we can make it a little bit complicated to say you also need to consider this dielectrical constant, this kappa not being 1 but being another value. Again, all you need to do is just to first figure out this capacitance of a single capacitor by considering this kappa effect. And then from here, you can continue to figure out the equivalent capacitance of multiple capacitor, like in this case, these two connected in series, but now this one, the kappa is, for this C2, kappa is 1 basically, while for this C1, this kappa is being another value, right? So this is, pretty much the topics about the capacitance. Okay, we can have like 10 minutes break and coming back for the next topic. Yes. Then? Charging what? Charging? Yeah, it will, of course. Yeah, but of course we don't consider that kind of special scenario. Or, as I mentioned, pretty much we only consider this kind of simple capacitor, parallel, two parallel plate. Yeah. How much max? 13, should be 13. 13. 13. Actually, this capacitance and capacitor pretty much is the topics we are going to test for the quiz 2. We do have the a quiz 2 for this part, and actually I want to ask whether we do it, let's say maybe next Friday or next Tuesday. Which time is better for you guys? If you next Friday means you need to come another day without lecture, without tutorial. Cannot be after, have to be before. No, before. So can you guys make it? Let's say we do it 6. Not next Tuesday. Not next. Yeah, if it's Tuesday, Monday or Tuesday, then it's going to be next Tuesday. If we do it, let's say 6 next Tuesday. Before lah, after 10 p.m. Huh? Oh, it's going to be 45 minutes. So let's say we start at 6 p.m. Yeah, 9 MCQ. The same format as quiz 1. Just exactly the same. Yeah, exactly the same format. Which one do you prefer, most of you? Tuesday. So you guys can make it for, let's say, 6 p.m. Okay. Sorry? Yeah, a little bit late, fine. No, I will book another venue. Yeah, and all the topics still the capacitance. Yeah. Sorry? No. Okay, if you guys prefer, then I will make an announcement. So that is for the quiz 2. Next Tuesday. Huh? No, anyway, the details I will announce in until then. Okay, so anyway, let's move on to the second part of the electricity and magnetism. That is about the magnetic field. And actually later you will find out the way we discuss electricity and magnetism. For most of the topics, you can make this one-to-one comparison. And also the structure we discuss it is also quite similar. Like here, first, the first topics we need to discuss. Is it a bit too loud? The first topic is the magnetic field. Just like the electrical field, we also have this magnetic field. And we will also discuss the magnetic field and magnetic force for two scenarios. The first scenario is the so-called one moving charge, one charge. Another scenario is the so-called current carrying conductor. Basically, it's a current flow inside the conductor. So now, before we discuss anything about magnetism, let me ask you the relation between these two scenarios. In one case, you only have one moving charge. In another case, you have this current flow inside the conductor. What is the relation? Forget about anything about magnetism. It's just generally what is the relation between these two scenarios. One moving charge, current flow. Sorry? Current flow is opposite moving charge. Yeah, all the charge. In one case, it's one charge. In another case, it's all the charge or is infinite number of charge. This is basically, you can say, relation or difference. So now if you can tell, actually, we are coming back another case of two scenarios, one and infinite. So you can tell that the way we are going to, how we are going to move from the second point to the third point, right? We have been doing this for single charge to infinite number of charge, right? Of course, for the electricity and for the electrical field. And now here we are going to do the same for the magnetic field and magnetic force. And of course, I think this should be something, at a certain point you may see something like this, this magnet bar, either on the fridge or some other types of magnet bar can give you this kind of image when you place the magnet close to this kind of magnetic particles. So basically, it's to say again, it tells you there's some kind of force between these two, right? And also there's kind of field surrounding the magnet, just like what happens in surrounding the charge, right? And in this case, is the so-called field is a magnetic field. Typically, we write with this B. Right? And the way we describe or visualize the B, we have the same, or very similar. We also have these magnetic field lines to visualize the magnetic field B. And the principle is also very similar. Of course, not exactly the same. Like here, for these magnetic field lines, first, it must start from N and end at S, the so-called north pole, south pole. So here, when we discuss charge, it's positive, negative. When we discuss the magnetism, these two polarity is the so-called north pole, south pole. Just the two polarity. So then the magnetic field lines must leaving this north pole and enters the south pole. And at each point, let's say here, this B must be tangential to this magnetic field lines. And also, you cannot have two magnetic field lines close each other for the same reason. And finally, the density of magnetic field line should be proportional to the magnitude of magnetic field B. So it's pretty much the same. And once we have these magnetic field lines and magnetic field, we can discuss the magnetic force. So now here, when we discuss the magnetic force, we always discuss a moving charge. Only when you have a moving charge, you will have a non-zero magnetic force. And this is the formula how you can quantify the magnetic force. This is the velocity V, and of course this is the magnetic field B. And both are vector. So it's the cross product of V and B. So that is why you can see from this formula, you can see this FB will be non-zero only when you have this finite velocity V, right? If it's a static charge, meaning if V is 0, then the force is always going to be 0, right? And here, because here it involves the cross product of two vectors, and actually this is nothing special about the magnetic force. It's just a general way to determine the direction of two vector cross product. For any two vector, this is how you determine the direction of the cross product. So you use your right hand. Make sure these three fingers are mutually perpendicular to each other. That is to say, in the three-dimensional coordinate x, y, z. So this is the first thing you do. And the second is you align this finger, your thumb, to the first vector. In this case, it's vector v. And align this middle finger to the second vector. In this case, is b. And this, this one will give you the direction of v cross b. The sum basically pointing along v cross b. So this is how you use the right-hand rule to determine the direction of the magnetic force. You don't do that, lah. So, of course, actually, to be more accurate, this only gives you the direction of v cross b. This is only v cross b, not necessarily fb. To determine the direction of fb, you also need to consider this q. If q is positive, then this is fb. If q is negative, then you need to reverse it to get fb. Right? Make sense? So this can be positive, this can be negative. For this cross product, you use the right-hand rule. Right? So this is how you determine the direction of magnetic force. For the magnitude, of course, it's just like any, again, vector product. Here is going to be sine theta. It's going to be sine theta. And if we try to make some comparison between this electrical field E and magnetic field B, electrical force Fe, magnetic force Fb. So you will have this, of course, this basic two formula. And first of all, you can see for this Fe, all you need is Q and E. For this Fb, you need Q, B, and also velocity, right? And the second is because of this kind of cross product. This cross product, you can see, if we consider the work done by electrical force and the work done by magnetic force. That is this one, right? This is the work done by a force. Force dot displacement, ds. This is the work done by the force, right? This is the case for the electrical force and also magnetic force. So you can see for the magnetic force, this is going to be always to be 0. Always to be 0. Whatever displacement you have, whatever velocity, magnetic field you have, this always has to be 0. Why? Why? Why this dot product always has to be 0? Sin 90 is 1. So this is the FB. This, if we write down this ds, again, displacement in terms of velocity, that is this one, right? Velocity times time give you the displacement, right? And you can see now it's the dot product of FB and V. So what is the direction? Relative direction between this FB and V. Remember, this is a V. This is a B. This is FB. So V and FB always must be perpendicular to each other, right? So then the dot product of these two must always be 0. Dot product is cosine theta, right? So now it's cosine 90, right? So this is why for the magnetic force, the work done by the magnetic force always must be 0. And here's some notation for you to know is because now actually we involve 3 directions. In practice, in order for us, we all label this direction consistently. Then we come up with this kind of notation. Basically, it's this kind of array of dots. Means the direction pointing out of the page, out of the perpendicular to the page and out of plane. Well, if you see this kind of array of clause, it means a direction pointing into the page, also perpendicular to the page. And here, this is just convention we all follow. Again, no physics reason. We always follow this kind of convention. Dots means point out of the page. Clause means pointing into the page. Okay, once we can determine the magnetic force, then one more step is we try to figure out how exactly a charge will move inside a magnetic field B. So let's see, first of all, in this space, there is this kind of magnetic field B. Again, when you see this kind of symbol, you should immediately tell the direction of B is pointing into the page, right? And if there is a moving charge, let's say a positive charge, moving with this velocity v inside the magnetic field B, then we know there will be a magnetic force which is given by this, right? Given by this. V cross B. So now can you, let's say, if you use the right-hand rule, you can determine this is going to be the FB in plane, right? And the way you do it is just QVB is going to be this. If it, right? This is a V, B is pointing into the page, and then this is V cross B. And also, in this case, it's positive charge. It's positive charge. Okay, maybe you can do it at this point. It's a bit more comfortable. let's say at this point, V, B, V cross B. Right? So you will find out actually, again, this FB is always perpendicular to this V. Meaning, if V is along different direction, FB is also along different direction. But they are always perpendicular to each other. And if you have this kind of scenario, what will happen to this charge? When you have a force that is always perpendicular to the velocity, what kind of motion you will have? It's going to be this kind of circular motion, right? It's going to be this kind of circular motion. And when it comes to a circular motion, you must always have a centripetal force, which is given by this mv squared over r. So v, the velocity of the circular motion, and r is the radius of the circular motion. M is just, of course, the mass of the particle, right? This is the general centripetal force. But in this particular case, of course, where does this centripetal force come from? It's coming from this FB, right? FB is maintaining this circular motion. Or another way to say FB is serving as the centripetal force. And FB, of course, equals this. So that is why you have this formula to define the circular motion for a moving charge inside a magnetic field B. And from this equation, so you can determine the radius of the circular motion, or you can also determine, let's say, the frequency, that is the number of a cycle for each second, the angular frequency, the period. Here, all those parameters are nothing special. It's just the typical parameter when it comes to a circular motion, right? Again, here the most important one is this. This is the most important equation. And of course, here we are considering a simple scenario where this V and B are perpendicular to each other. It's 90 degrees. So if they are not, actually, let's say you have B along this direction, and let's say here, if this is your B, this is your V, and this V and B, they are not perpendicular. Of course, still, based on this one, you will still have finite finite FB, right? But in order to figure out the resultant motion inside this magnetic field, actually, we can try to decompose this vector V to two components. Again, of course, V is a vector, and for any vector, you can decompose, let's say, this Vy component, which is perpendicular to B, and also Vx component, which is parallel to B. You can always decompose in this way, right? So now, if we can only consider this Vy and B, then basically it's a scenario like this, right? So means if we rewrite this, if we rewrite this one for this particular case, then it should be Q V y B equals m V y square over r, right? Well, for this Vx component, you can see if it's the Vx component, let's say if you consider this Vx cross B, what do you have? Vx cross B, what do you have? Vx cross B, again, Vx is parallel to B. It's going to be sine 0. This is going to be 0, right? That is to say, actually, if you only have this Vx and B, there's no force on this particle. There's only initial velocity of Vx, and then there's no other force. So what will happen to this? If it's only Vx and B, what kind of motion you will have? Yeah, it's just a linear motion with constant velocity Vx, right? So overall, basically what you will have is here a circular motion defined by this, and another linear motion defined by this Vx, right? So of course, in reality, these two add together will give you this kind of so-called helical motion. It just, let's say, basically is something like this, right? The so-called helical motion. Vy is perpendicular to B. We purposely decompose the V to these two components, one perpendicular to B, another parallel to B. Which one? Vy? Yeah, if you say, if you make this to be theta, let's say if you make this to be theta, then it's going to be V cosine, Vy is V cosine theta. Yeah, I mean, again, depends on how you, which angle you are using. If you use, let's say this one, if it's, let's say this is theta 1, this is theta 2, then it's going to be V sine theta 2 is V1. Vy, sorry, Vy equals V cosine theta 1 equals V sine theta 2. And if on top of the magnetic force, there is also electrical force, of course, now you can see basically for any charge, we may have two forces, one electrical force, another magnetic force. And for this example, if we when you try to measure this magnetic field B, electrons are accelerated from rest through a potential difference of this value, and then they are observed to travel along a curved path with radius of this value upon the application of magnetic field B perpendicular to the electron. Ask you to determine again the magnitude of this B. So again, if you still remember the way we do it during the tutorial, the so-called first, you identify the physical picture, which in this case is to say you have an electron, initially there is a velocity and enters a magnetic field. And this electron is making a circular motion inside the magnetic field, right? And this is a physical picture. And while for the next, the involved physical process, we can identify two processes. This is the process 1, right? Electrons are accelerated from rest through a potential difference of this value. And the second process is just here, a circular motion of this radius inside this B. This is the second process, right? So then we can try to write down the either defining equation or the physical understanding for each process. For the process 1, it's just an electron acceleration under a potential difference. For this one, this is the so-called equation, right? The acceleration or the work done by the potential difference will make this electron to gain certain kinetic energy. This is the so-called accelerate, right? The acceleration basically means there's an increase of kinetic energy. And this is how you define kinetic energy of a moving particle, right? So this is the equation for process 1. And also for the circular motion, of course, you have this one, you have this one. So you combine these two, you can figure out this, the magnitude of B. So now, until now, it's the magnetic force on single moving charge. Now we are going to move on to the next scenario, the so-called current carrying conductor. Again, as we mentioned at the beginning, the difference is now we are going to deal with infinite number of moving charge. Right. So let's say if here you have this kind of external magnetic field, if there is no current flow, of course, then there will be no magnetic force. No current flow means, let's say you may have one electron moving along this direction. You will have another electron moving along the opposite direction, right? So while for each electron, still you will have finite FB. But these two electrons, FB, is going to cancel each other. So overall, if you don't have a current flow, you will not have a magnetic force. Right? And if you have finite I, then you will have the finite magnetic force. And if you reverse the direction of I, basically it's you reverse the direction of moving charge. Of course, you are going to reverse this direction of FB, right? And the way we can derive the magnetic force actually is still based on this one. Based on this one. Again, FB for the moving charge. But of course, again, one more step you need to do is to build up the relation between Q and I. Q and I. And here for this step, I will just skip, instead to give you the final formula. The FB, the magnetic force on a current carrying conductor, E equals ILB. And I, of course, is just the magnitude of the current, B the same. While for this vector L, first of all, the magnitude is just the length of the wire. the direction of this vector L follows the direction of current flow. So this is how we define this vector L, the magnitude and direction. The direction of vector L is the same as the direction of current flow. So if you have this formula, then you can see here you also have this vector L cross vector B. You will also need to use this to determine the FB. And of course, this basic formula is only valid when all are uniform. Constant I, constant B, and constant L. Only when these three all are constant, then you can apply it directly to get this FB. And if any one of them is not, then again, we will come back to this idea of integration. Let's say you have this kind of curved wire. So now and there's a current flow, let's say along this wire, along this direction. So now the B along this direction constant. For this current flow, can you apply this one directly? ILB, can you apply it directly? Or another way is to say for this curved wire, on this entire wire, is it I constant, vector L constant, B constant, B constant, I constant, L, vector L? No, right? Again, the way we define vector L is it should follow the direction of I. That is to say, actually, here this is a vector L, and here is vector L, here is vector L. Basically, the direction of vector L is keep changing. Then, of course, this vector L is not uniform. And if this is the case, you will not be able to apply this directly. But instead, if we only look at this tiny section ds, then we make this, again, this ds to be a very small section, very short section. Then for this, only for this ds section, we can tell I uniform, B uniform, ds is also uniform, right? Then for this ds section, we can apply it directly. And from ds section to this entire wire, again, physically is you just need to do this integration. And the result should be the total force on this entire wire, right? And if we apply this idea, let's say if we have this kind of wire, starting from point A and here to point B. And so what you need to do is to do this integration from A to B. And that will just give you this vector pointing from A to B. Yes? Okay? Velocity of, there is no velocity here. We don't have velocity here. We only have current flow. 13. Yes. Or yes, if you consider this direction of current and direction of moving electron, of course, they are opposite. Yeah.
Let's say, because your this one say it must be a straight wire, so if I make it become a circle, so technically it's not a straight wire, but I still can count when I use the forward arm.
Yes, then.
So even though it's not a straight wire, but I still calculate the
Yeah, this is exactly the point here. You can find out an effective straight wire to do this calculation. That is here, let's say this, whether it is this kind of straight wire directed from A to B or this kind of curved wire from A to B, actually the vector, the length vector, vector L is the same. Because again, if it's not a straight wire, you do this kind of integration, basically it's still a vector pointing from A to B. Again, if you, let's say, you have these two vectors, the vector sum of these two vectors is just this one, right? And the same, you can do it for even basically infinite number. There's a here, then the sum is also going to be here. And you can continue, that is the case here. So eventually it's just going to be a simple vector directly pointing from starting point to ending point. And even more special scenario, if you make the starting point and ending point the same, basically start from here, coming back to this point, then it's a circle. Then this one must be 0, right? So that is to say the total magnetic force inside a constant B for a closed loop must be 0. So makes sense. And for this example, what you have is a wire with a semicircle portion and also a straight line portion. There's a constant I. Ask you to figure out the magnitude and direction of FB on these two portions, curved portion and straight portion, right? So if you still remember this, then immediately you can tell, let's say this F1 plus F2 should be 0, right? The net force should be 0 because it's just a closed loop. And you can do it either on this straight wire first, that is, actually if you just look at this straight wire, for this straight wire, this portion, I, L, B, all are uniform, right? So you can use it directly to figure out this one. And while for the curved portion, it should be the same magnitude. But for the direction, again, you have to use this one. Let's say if we look at the straight line, then this is going to be the vector L. This is going to be the vector L. This is going to be B. So it should be like this. So this is FB pointing out of the page. I, or vector L, follows the direction of I. And B is pointing up. So it's pointing up, so it's like this. So this is going to be the FB pointing out of the page. Right. I mean, this one you have to practice. In some cases, it's not so comfortable to do it. Okay, so this is about the magnetic field and magnetic force. And next topic we are going to discuss is where this magnetic field B comes from. And this is the so-called the source of magnetic field. And if you do this kind of simple experiment where you place this compass, this is a compass which basically can detect a magnetic field, right? Pointing along N or S. You place this kind of compass needle close to a wire. If there is no current flow inside this wire, you will find out basically you will have this kind of alignment. So do you know why a compass needle always aligns in this way? Why always the so-called pointing to the north? Forget about this wire. Why the magnetic field of so magnetic field from where? Yeah, magnetic field from Earth. That is why if you don't have anything else, always you will have this compass needle pointing along this direction. But when you place it close to this wire, if you send in a current flow, you will find out this compass needle, it will be rotated. Rotated basically, of course, immediately it tells you when you send in a current in the wire, you generate a magnetic field B. And this is the key understanding you can derive. That is to say, when you have I, you can have a B. Right? So what we are going to do next is to see how we can quantify this relation. Okay, the starting point again, if we look at the, try to compare this electrical field E. E starts from Q, right? E comes from Q. And this is a formula. Here, whether you have this Q to be a static or moving doesn't matter, right? And if you have this to be a moving charge, then this moving charge will give you a B here. So this one tells you even you only have one moving charge, you will have certain finite B, right? Of course, the details of this one I will just skip. Let me first, we try to build up this, all this connection first. If you have one moving charge, you can get finite B. Then how can you determine B due to a current flow? Again, now let's say we start from here. You have B due to one moving charge. Now we need to determine B from a current flow. Again, the relation between these two. One charge, infinite number of charge. One moving charge, infinite number of moving charge. Right? Basically, to say you just add up all, you should get this B due to I. Right? But of course, again, in practice, it's not just add up. You will need to do this integration. And you will find out this is B due to a current flow I inside a wire of length ds. Right? And of course, the distance is always relevant. The distance r. So this is how you can build up this magnetic field B due to a current flow I. And again, this simple formula it's only valid when all those parameters are uniform. And if, let's say, if you have this kind of curved wire, then you can see this ds and this ds and this vector r all are not uniform. Basically to say, here is ds1, here is vector r1, here is ds2 and vector r2. Both are not the same. So that is to say, if you have this kind of wire, actually both ds and vector r are not uniform. You cannot apply it directly, but instead you will need to do integration from ds to entire wire. This is what you will get. You will get this total B. Total B. Of course, these two slides are here again just to give you the logic chain. The details you don't need to, you can just ignore it. So the key idea is we start from a single moving charge to a tiny section of current flow. And from this tiny section of wire to any kind of finite size wire. So 1, 2. And this is the final formula. Again, for those all the details in these two slides, you don't need to bother yourself if it's too complicated. Yes? Again, all the formula will be provided. Actually, now you can already see the formula we are going to provide from the NTU Learn. I think that is already uploaded. So basically, you will get the same formula sheet during the exam. And if we apply this idea to this question to find out the magnetic field B due to this kind of straight wire with finite length L, there is a constant current I, then you can see even for this kind of straight wire, we cannot apply this formula directly because, well, this ds here all are the same, but the vector r is not the same. Vector r is not uniform. So you cannot apply it directly, but again, you can only apply it for this tiny ds section. And you have to do this integration, let's say, from one end to another end, that is here. That is here. And you will find out the B. And the theta 1 is just, this is the theta 1, and this is the theta 2. Again, I guess for this slides, you can also just ignore. This so-called Biot-Savart law gives you a general idea how you can, in principle, to determine B due to any kind of I, any kind of Y. Of course, in practice, we will only handle some kind of special scenario. Okay, so one more point is about this direction. Here, this just gives you the magnitude of B. And the way we determine the direction of, again, pay attention, now here we are talking about this, the direction of this B. Then we have another kind of right-hand rule. It's also the so-called right-hand rule. Now what you need to do is to align your thumb with the current I. And then this forefinger, you curl this forefinger, it will give you the direction of B. The B will follow this direction, how you curl this forefinger. That is why if you look at this case, this is I, so you curl this forefinger, means on this side it's pointing into the page, and on this side it's pointing out of the page. So this is how you use another kind of right-hand rule to determine this. So basically now we have two kinds of right-hand rule. One is to determine this. Another is to determine this. Determine this B. B coming from I. And this is also something for sure it will be tested. You don't need, you need to make sure you don't get confused. Again, these two, this is V cross B, V cross B. And this is I will give you this kind of B. Of course, this I, whether V or L, the same. These two are the same, right? I mean, anyway, it's just the cross product of two vectors, right? And for this example, actually, we did something similar for the electrical field E and electrical potential V. Now we are going to do it for this B. In this case, you have this kind of loop current and ask you to determine the B, magnetic field B at this point, right? Again, of course, first of all, we can tell this is a non-uniform I, so a non-uniform ds, and also non-uniform vector R. So what the starting point will only give you the dB due to a tiny section ds. And from here, you will need to do this integration along this entire loop to get this total B. So on top of this, of course, there will be some kind of mathematical calculation. Okay, later I will talk about actually what are the more relevant scenarios. This is considered quite complicated. This one. So now we are talking about this so-called, the meaning of this means the integration along this entire loop. Again, the so-called ds is just tiny section along this loop. So you have this ds1, ds2, ds3, ds4, ds5. Then you add up all together. Basically, is the length of this loop. No, here is just ds, not vector ds. Here is just ds, not vector ds. And based on this result, of course, you can look at some special scenario. That is, if you make this x to be 0, that is at the center of the loop, you can find out this one. And if you make this to be infinite far away, that is x much larger than this r, you can find another equation. Again, all this is not to say you don't need to memorize anything. This is just to give you an idea. Even for this kind of complicated current source, the way we do it is still the same. Okay, next, Ampere's law comes to the most important part for this topics of how we can determine P from I. So far, the way we introduced again is by the kind of applies to any kind of I. Any kind of current source, in principle, we can do it, define ds and do this integration. But for us, more relevant scenario is some special case. And those case is where we can use this so-called Ampere's law to figure out P due to I. And the Ampere's law basically tells you if you have, let's say, multiple current source I1, I2, I3. And if you need to figure out the P at a certain point, let's say P at this point, all you need to do is you construct an Ampere's loop. Let's say, of course, if you only want to figure out this P at this point due to I1 and I2, then all you need to do is to construct a loop which only includes I1 and I2. Only I1 and I2. Because now we are talking about P at this point due to I1 and I2 only. So you construct this kind of loop. And if you do this integration of P dot ds and along this entire loop you just construct, the result will be this constant mu naught times I, and this I is the net current enclosed in your loop. This is the so-called Ampere's law. So here you see you need a loop. You need a loop. It's a two-dimensional loop. In the Gauss's law for the magnetic field, it's a closed surface. It's a three-dimensional surface. So if you remember when we talk about this Gauss's law, it's E vector dA equals this Q in over this constant, right? This is a Gauss's law for, yes? Yes? No, we will come to that later. It's not. Here, this is again the Gauss's law for electricity, and this is Ampere's law for magnetism. So again, you see the difference. This is the dA, so means you add up all the area, you get a three-dimensional surface. While here is a loop. You add up all the ds, you get just a two-dimensional, the length of a two-dimensional loop. So this is Ampere's law. And if we Let's say consider the different scenario. Just like here, the charge, you need to consider positive charge and negative charge. Positive and negative, they will cancel each other. Similarly, for the current flow, you also need to consider the direction. Of course, same direction, just add up. If opposite direction, they need to going to cancel a little bit with each other. So like in this case, I1, I2, opposite direction, then it's going to be I1 minus I2. So you also need to consider the direction. So for your question just now here, this one, of course, if you just do this, this is going to be 0. But this being 0, this one does not necessarily be in 0. Because you have this b is also is not a constant. This vector b is also going to be different. Let's say the b at this point is not the same. So you cannot just write down this as, let's say, b times this ds. These two are not equal. Because again, if you do in this way, it means the b is constant along this entire loop. But it's not. So you cannot do in this way. So these two are not equal. So that is why this one, yes, is 0, but then the dot product of these two, the integration is not 0. And actually later, for some examples, you can see exactly how we do it. And let's say we look at this example, where you have a long straight wire, that is this one, this yellow wire, radius r, carries a steady current I0 that is uniformly distributed through the cross section. Ask you to calculate the magnetic field at the distance r from the center to the wire for two scenarios. One is here outside the wire, another basically inside the wire, right? So of course, still, if you don't have this Ampere's law, then the only way you can do it is you will do this kind of integration, which can be very complicated. But if we do it based on the Ampere's law, so the way we do it, in order to use the Ampere's law, the first thing is you need to construct that loop, the so-called Ampere's loop. And just like the way you construct the Gaussian surface here, this is a Gaussian surface, and also the way you construct this Ampere's loop, first, it will require you to have some intuition plus some practice. And second, for us, for you guys, actually, you only need to be able to handle the scenario we discussed either during the lecture or the tutorial. Meaning you will not be required to handle any kind of new scenario during the exam. Let's say for this kind of wire, then the so-called Ampere's loop is going to be this one. If we are doing the first part outside the wire, then we should construct an Ampere's loop like this, which is concentric to this wire. but the radius is larger. So this is going to be a proper Ampere's loop. The step 1. So now is we need to apply the Ampere's law on this particular loop. So basically it's to say this integration should equals this one, right? The Ampere's law will directly tells you this, because now the net current inside the Ampere's loop is just the total current, right? This is the step 1. And step 2, let's do some more about this integration part. The B, let's say if we look at this point, this is going to be the B, this is going to be the DS. They are going to be parallel, right? And if you look at this point, you will find out B and DS also parallel. And the same for any point on this loop. That is to say, for any point, it's always cosine 0. Always cosine 0, that is 1, right? So this is if you label this as step 1, then this is a step 2. And we are doing this step 2 based on physical understanding. We are not really doing any mathematical calculation, right? The physical understanding is just to say at any point on this loop, B and DS always parallel. And this is step 2. And step 3, from here to here, anyone can tell me why this is valid? Again, from physical point of view. No, we are talking about step 3. Why this step 3 is valid? What's the physical reason? Yeah, B is constant. The magnitude of B is the same for any point on this loop, right? That is why for the integration, you don't need to do anything for a constant. Instead, it's just the integration of ds. And again, here is just not vector ds, just ds, right? And finally, from here to here, just like the question you asked, the integration of ds along this entire loop is just going to be the 2 pi r, right? And finally, you build up this relation. So step 1, 2, 3, 4. And eventually, you can figure out this B. Again, you can see for each step we are doing this based on certain physics understanding. And for another scenario, if it's inside the wire, then the way we do it is similar. If you need to figure out B inside the wire, then of course you will need to construct this Ampere's loop also inside the wire. Also inside the wire. Then this one equals this one. Right? Step 1. And for the same reason, step 2, step 3, you can see whether this loop is inside the wire or outside the wire. As long as these two are concentric to each other, then all these are the same. The only difference is now here is this total I naught. Here, this I basically is only going to be I in this section, not the total I. Right? That is why you need to figure out the I that penetrating through the Ampere's loop, which is by this ratio, by this, a part of this total I naught. Right? So, and eventually you can find out this is a B inside this wire. Okay, again, for the determination of B from I, apply the Ampere's law to do it is the most relevant part. Is the most relevant part. Of course, we also, even for the magnetism, we also have this Gauss's law. And of course, if you need to build up this Gauss's law, you will need to do something similar. First, you will need to define the magnetic flux in exactly the same way, from E dot A to B dot A. And if you want to figure out the flux through a closed surface, you will need to do this integration. And now but for the magnetism, the integration of this one is always going to be 0, as long as this is a closed loop. This integration is always going to be 0. Anyone can tell me why? For any kind of B and any kind of closed surface. As long as it's a closed surface, then that one must be 0. Okay? Same thing like displacement. But over there is to say the displacement is to say this force and velocity always perpendicular. But here, does it mean you are talking about B always perpendicular to A? No. We are talking about any random closed surface. So 2 points. First, the physical meaning of this is just the magnetic flux, right? This is just the magnetic flux. And the magnetic flux is just a measure of how many magnetic field lines penetrating through a surface, a closed surface or open surface, right? This is the point 1. And the second point is for the magnetism. We just mentioned the magnetic field line always leaving the North Pole and coming back to the South Pole. And now the special thing is for the magnet, this N and S always come in pair. Not like the electrical field, you can have separate positive charge, only one positive charge or only one negative charge. You can separate them. But for the magnetism, the North Pole and South Pole always come in pair. You cannot just have this North Pole or you just have this South Pole. That is not possible. If always you have this ns at the same time, then you can see actually the magnetic field line is always a loop. Is always a loop, leaving from N, coming to S, and then inside from S to N, forming a loop. And if the magnetic field line is always a loop, then you can see any kind of closed surface. There will be one point for the same magnetic field line. There will be one point entering the closed loop. There must be another point leaving the closed loop. Right? And that is to say, the net number of magnetic field line penetrating through the closed surface must always be 0. And that is the meaning of this. Right? The magnetic flux through a closed surface must always be 0. Okay, we have one more question. Where there is a rectangular loop with a length A times B, this is a rectangular loop, near a long wire carrying current I, and the distance between the wire, this is the C. The wire is parallel to the long side of the loop. Ask you to find out the total magnetic flux through the loop due to the current in the wire. So here there is I, right? So basically there is a current flow I, and there is a rectangular loop. Ask you to determine the magnetic flux inside the loop. Again, then the immediate formula will be this one, right? This is the flux by definition. And this one, just like any formula, it will only apply to the scenario where both B and A are uniform. So now you tell me, in this case, is this A uniform? Yes or no? For this, the vector A for this rectangular loop, is it uniform or not? Why? You guess. No, just the loop itself. Yeah. No, how do we, here there is a rectangular loop. How do we find out this vector, surface vector? Just like we did it for the Gauss's law for electricity, right? No, forget about this B or E first, just this vector A. First of all, this vector A, the magnitude of this vector A is just the area of this loop, which in this case A times B, a rectangular loop, right? Then how about its direction? And this direction, is it constant? Yes, no? Yes, right? We are just talking about two-dimensional loop. Then it only have one surface normal, right? So the vector A is uniform. Then how about this vector B? If you want to figure out whether it is uniform or not, of course, then another question is where it comes from. Where it comes from, because there is no external B, right? This B can only come from this I. That is to say, here, This is going to give you the direction of B, right? Pointing into the page. Then how about the magnitude? Yeah. You need, if you want to figure out this whether this vector B is uniform or not, you must make sure same magnitude, same direction everywhere. That is the so-called uniform, right? This one will tell you, yes, it's always pointing into the page for this entire space. Same direction, but the magnitude, this is the magnitude, right? Just like actually very similar to this one. So now you tell me based on this one, let's say at this point is B1, at this point is B2. This B1, B2 we already know same direction. How about magnitude? Is it same? Just 2 points. Just these 2 points. B1, B2 are the same? Why? Yeah, here you have this, you can see this B is also a function of R. That is to say, this distance or this distance. Distance is different than this B1, B2, not the same. That is to say, now we figure out actually vector A is uniform, but vector B is not, right? So if one of them is not uniform, then we cannot just use B times A to get the total flux, but instead, even the entire one is not uniform, we can construct this kind of tiny section as long as we make this width of this section dr infinitely small. Then inside this tiny section, we can consider the B is uniform, right? And that is to say, we should be able to apply this B times A directly to figure out the flux inside this tiny section. And one more step, how you can get this flux through this tiny section to the total flux through the entire loop. Integrate, right? So that is to say, basically, you need to add up all those different tiny sections, right? So based on this kind of understanding, then first we can define, let's say, this tiny section with a width of dr and distance to this wire is r. Then this is going to be the B inside this tiny section, and this is going to be the dA, right? And from here to here is just you do the integration from one end to another end. One end r equals c, another end r equals a plus c. Right? So finally, you find out this total flux. Again, like in this question, step 1, step 2, and this step 3 are the so-called physically meaningful process. Okay, we are exactly on time, and that is all for today. Yes.
Why not ADR?
Where? Here? You mean here?
Now I'm thinking DA equals to B times PR. Why not DA equals to A times PR?
Let me.
Because my PR,
This is the DA. This is the DA. And A times PR. DR is this section. DR is the area of this section. So this DA is the area of this section. Yes. 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 The vertical, the width is dr. You can say the length or the height is b. What do you mean you use width to do the calculation? You mean you kind of define a section like this, this one. And you think, does it still work? No, first of all, then if you define this tiny section as that one, you need to first figure out if this both B and DA are uniform. It's not right. Because again, then B at this point and B at this point is not the same. The whole point of defining this tiny section is you need to make sure the simple formula is valid, means all the parameters are uniform inside that tiny section.
I think your prof arranged just before lab. Yeah, but no more lab already.
Oh, you guys. But the lab is only this week, right? The final lab.
I think week 5, correct.
Yeah, it's only this week. I don't think you guys can be ready lah. So give some more time to prepare. Yeah.
Should be 23rd.
The lab session is this week Friday, right? This week. So you cannot make it. I don't think you guys have enough time.
But sir, you're almost wrapping up your topics already. Next week still got your lecture, right?
Yeah, we still have.
This is the last topic.
No, we still have some new topics next week. Then plus some review lecture next week, then that is all. You think you are ready by this Friday?
No. I want to start preparing.
That is why I tried to
2 weeks from this week, right? Not the.
Yeah, 2 weeks, yes. Yeah, next 2 weeks, exactly 2 weeks. Same format, 9 MCQ.
Oh, yeah. Yes. Let's go.
Okay, bye.
Prof, tomorrow 8 p.m. still okay, right? If you finish it.
Okay. Okay.
Try that.
Mm-hmm.